to get an astrophysicist explanation of the literal three-body problem without reference to anything that's shown up on streaming services.
And that means he's not going to ruin the show for you.
I don't know anything about the show, but I do know enough to describe the three-body problem to you coming up. Let's start simple.
Okay.
Okay. So as we know, the moon orbits the Earth.
Right.
But that's not the right way to say it.
Okay.
Okay?
All right.
The moon and the Earth orbit their common center of gravity.
Ooh.
So Earth is not just sitting here.
Right. And the moon is going
around it. They feel in their common center of gravity. You know where it is? It's 1,000 miles beneath Earth's surface, along a line between the center of the Earth and the center of the moon.
Got you.
So as the moon moves here, that center mass line shifts. Okay?
Mm.
So that means Earth is kind of jiggling like this as the moon goes around.
Gotcha.
That's their center of mass. All right. This is the two-body problem. It is perfectly solved using equations of gravity and mechanics.
Makes sense.
Perfectly solved.
Yeah.
Isaac Newton solved it.
Okay.
My boy.
That's your man.
So that worked. Then Isaac applied the equations to the Earth-Moon system going around the sun.
Okay.
Okay? That worked too. So in that system, let's ignore the moon for the moment. It's Earth going around the sun, another two-body system.
Another two-body system.
All right? But then he worried. He said, every time Earth comes around the back stretch and Jupiter's out there,
right?
Jupiter but tug on it a little bit.
That's a lot of gravity.
A little bit, tug on it as we come around back the other side.
What's up, Earth?
All right. And then it comes around again, tugs on it again.
What's up, Earth?
Right. And, of course, everybody's moving in the same direction around the sun, so the Earth would have to go a little farther in its orbit to be aligned again with Jupiter, but it's going to tug on it.
Right.
Okay. He looked at all these little tugs, and he says, I'm worried that the solar system will go unstable.
Right.
Because if it keeps tugging on it, it keeps pulling it away. And the previously stable orbit would just decay into chaos.
Okay.
Okay. He was worried about this.
Okay.
You know what he said? But I know my stuff works, and it looks stable to me.
Right.
So clearly it is stable, even though it looks like maybe it wouldn't be stable. You know what he says? He said, every now and then God fixes things.
Well, there you go.
That's the answer.
Even Isaac Newton. Wow, look at that.
Yeah.
When in doubt.
When in doubt.
Just let God figure it out.
Right. I can't figure it out.
God did it.
Clearly, we're all still here, and we haven't been yanked out of orbit by Jupiter.
Right.
But Jupiter is pulling on us.
So it's a God correction.
God correction. Okay. This is the first hint that a third body is messing with you.
Right.
Okay? In some way that maybe is harder to understand.
Mm-hmm.
Fast forward 113 years.
All right.
We get to Laplace. He studied this problem.
Right.
Okay? And he developed, I don't think he invented, but he developed a new branch of calculus called perturbation theory.
Aha.
Okay? Unknown to Newton, even though Newton invented calculus.
Right.
He invented calculus.
Right.
All right? So he could have done it. He could have said, in order to solve this problem, let me invent
more calculus.
More calculus.
I just need more calculus.
I just need more calculus. He didn't do it. Didn't do it. So Laplace develops perturbation theory, and it comes down to we have two bodies, the sun and the Earth in this case, and the third one, the tug is small, but it's repeating. It's not a big tug. Jupiter's not sitting right here.
Right.
It's way
out there.
Way out there. It's just a little tug. And so you can run the equations in such a way and realize that a two-body system that is tugged often by something small, that it all cancels out in the end.
Gotcha.
Okay? So when it's out here, the tug is a little bit that way, but now it's over here, and the tug is less.
Right.
All right? And then sometimes it's tugging you in this direction when that's the configuration. You add it all up, it all cancels out.
And it just
But
cancels
Newton could not have known that without this new branch of calculus.
Okay.
Okay? Perturbation theory. So that took care of that third body.
Gotcha.
Where solar system is basically stable, okay, for the foreseeable future in ways that Newton had not imagined, in ways that Newton required God.
Right.
Okay? Oh, by the way, just a quick aside, we're up to the year 1800. You know who summoned up these books to read them immediately? Because there's a series of books called Celestial Mechanics.
Okay.
Napoleon.
Ah, I am Napoleon.
Napoleon, who read all the books he could on physics and engineering and metallurgy.
Man, look at that.
Okay, he wasn't just a tyrant.
Right.
He was like
It was a smart tyrant.
Smart tyrant. All right. So he summons up the book. Doesn't have to be translated because they're both in French.
Right.
He reads it, goes to Laplace and says, Monsieur, this is a beautiful piece of work, brilliant, but you make no mention of the architect of the system. He's referring to God. And Laplace replied, Sir, I had no need for that hypothesis.
Ooh, that's a mic drop. Ooh, that is tough. Man.
That's a dig on Napoleon and on Newton.
Yeah.
And on Newton.
I have, oh man, look at that. Yeah,
all right. So let's keep going.
Go ahead.
So now, let's say we have not just the planet and one of its moons, but let's say we have a star and another star, double star system.
Right.
Famously portrayed in what film?
Star Wars.
Star Wars.
Yeah.
All right.
Of course.
So those two suns and the planet is stable, and I'll tell you why in a minute. But if you take a third sun and put it there, about approximately the same size, then what kind of orbits will they have? Give me two fists here, okay? So I'm feeling this one, but now I feel that where's my gravitational allegiance?
Right. You don't know where to go.
Am I going to come through?
Right.
But then am I going to go that way or this way? So I'm coming into the system. And do I go to you in orbit? But wait, you're still coming around here.
Right.
Now I feel this. And so it turns out the orbits of a three-body problem are mathematically chaotic.
Yes. I was about to say, that did not seem very stable.
Something has to give.
Well, this is in the series. What we're talking about.
I haven't seen the series.
I know.
I'm just saying something has to give.
That's all.
Two of these are going to collide.
Right.
One is going to get ejected.
Right.
Okay. That is the classical three-body problem. Three objects of approximately similar mass trying to maintain a stable orbit. And it goes chaotic with just three objects.
Look at that.
It is an unsolvable. Let me say that differently. You can calculate incrementally what's happening and track it until the system dies or splits apart or whatever. But you cannot analytically predict the future of the three-body system, because what chaos will do for you in your mathematical model is if you change the initial conditions by a little bit, the solution diverges.
Further down the line, it goes
crazy. It's not just a little bit different later on down the line.
Exactly.
It is
exponentially different.
Correct.
Wow.
With the smallest increment of distance.
Right.
So I'll say, I'll move you in this direction in this model, and then in a slightly different direction in the other model, it goes chaotic. That's what we mean by chaos.
Right.
Okay.
Okay.
It's mathematically defined.
Okay.
Okay. So now there's something called the restricted three-body problem.
Oh, right. Okay.
Okay.
All
The restricted three-body problem.
Never heard.
You have to give me your two thing back.
The
okay.
two planets.
You got that. Okay.
Two bodies.
You got your two bodies. Now the third body is little.
Aha.
Now you two will orbit each other.
Right.
Okay. And then this, it's not messing with them.
Right.
So there's restricted three-body problem. We have two masses of approximately equal and one that's much less than the other two. That is solvable.
Right.
It's called the restricted three-body problem.
Gotcha.
In the Star Wars case, that's the restricted three-body problem.
Right, because you have the two stars and you have the little planet.
The little
So
planet.
it's no
There it
big
is.
deal.
And it's even better because the planet is so far away that it only really saw one merged gravity of the two stars.
Right. Okay.
You're far enough away. That difference is not really mattering to you. You maintain one stable orbit around them both.
Around both stars.
Both stars. Okay? Now, if it got really close, then you'll have issues. Because then it does, again, gravitational allegiance matters. The stars are not going to care, but you will, because you'll get eaten.
You don't know where to go.
You don't know where to go.
I'm in love with two stars, and I don't know what to do. Which way do I turn?
So anyhow, so the three-body problem, the takeaway here is it's unsolvable.
Yes.
Not just because we don't know how to do it yet, because it's mathematically unsolvable.
Built into the system.
The system is chaotic.
Yeah.
Okay? Unless you make certain assumptions about the system that you would then invoke so that you can solve it. And so one of them is a small object around bigger ones. Another one, oh, by the way, in this solution with Jupiter out there, slightly tugging.
Right. Yes.
It turns out over a very long time scale, this is chaotic, but much longer time scale than Newton ever imagined.
Okay.
Okay? Because, yes, we are small compared to the sun, but Jupiter isn't. All right? And we're trying to orbit between them.
Right.
Right? So that's all. It's not deeper than that.
It's not there. Yeah.
Right? I could have said the 4-body problem, but this problem begins at the 3-body problem.
Right. Because you're going to have the same thing in 4 bodies or
Exactly.
5 bodies. It's going to be the same.
And we have star clusters with thousands of stars in them, and they're all just orbiting. We can model it, but we cannot predict with precision where everybody's going to be at any given time.
Okay.
Because it's chaotic.
The chaos. So it's basically it's about the chaos.
It's about the chaos.
It's all about the chaos.
Yeah. So what we do is we model the chaos.
Right.
Right. We say this will be statistically looking like this over time. You're not going to track one object through the system for eternity. That's not going to work.
That's so cool.
Yeah. All right.
That is so cool.
There it is. All right. Another explainer slipped in torn from the pages of science fiction.
Yes.
Just a simple description of the 3-body problem. Until next time, keep looking up.